In this segment, I want to talk about standing waves. And standing waves give rise to some really interesting phenomena, as we'll see. In a previous segment, we learned that waves can either add constructively, where their amplitudes are in the same direction, or destructively, where their amplitudes are in opposite directions. Let's review that idea really quick. If I have wave number 1, and it comes in like this, and wave number 2, I'm going to add that to wave number 2, and wave number 2 looks just the same. And wave number 2 has the same shape. Notice that my peak aligns with a peak, my trough aligns with a trough. If this is the amplitude of this wave, and this is the amplitude of this wave, then these two waves will combine to make a wave that has an even greater amplitude. It would look something like this, where now this wave has an amplitude of 2a. Okay? And so recall that we call this constructive interference. So that's constructive interference. We could also say that these two waves are in phase. And so that's a term we haven't used yet. Again, the displacements are in the same direction, so these two waves add. We call that constructive interference. They are in phase. Now, that's not the only way that waves can combine. Now, instead, imagine that we have this same wave, and it's going to combine with another wave from another source, but that wave is flipped upside down from this wave. And so that wave looks like this. Notice that it is upside down. Let's just say it's got the exact same amplitude, but it's inverted. Well, what happens when I add these two waves together? You know what I get? Nada. Okay, so I get just a flat line. In other words, the waves perfectly cancel out. We call this destructive interference. And we could say that these are perfectly out of phase. Again, a bit of new terminology. These waves are out of phase. They cancel. This is destructive interference. Now, there's an infinite variation between completely out of phase and completely in phase. We're not going to get into too many of the details there. I may ask you questions. Are these two waves in phase, or are they out of phase, or are they something in between? You'll see what I'm talking about as we go along here. So no new ideas, just a little bit of new terminology. Let's see how these ideas apply to standing waves. Well, what is a standing wave? I've demonstrated this once before, but let's just remember, right? I could send a wave down this string like that, and we would call that a traveling wave. We get a sense that it's going somewhere. Or I could create a standing wave, which looks like this. Yeah, it's kind of wave-like. Maybe that doesn't look that much like a wave to you. But probably if I did the two-lumper, it would. That looks more like a wave. But we don't get the sense that it's going anywhere. This is not a traveling wave. This is a standing wave. And we can think of a standing wave as occurring when the incident wave and the reflected wave are in phase or experience constructive interference. Let's look again at the wave and its reflection. You see how it goes down and it bounces back? Notice something interesting there. The reflected wave is inverted from the incident wave. When it hits the end of the wall there and bounces back, it inverts, it flips upside down. Check it out again. So when it's traveling to the right, its displacement is up. When it's traveling to the left, its displacement is down. Now, if I time my wiggles just right, I can get those two waves to be in phase, and we get constructive interference, a standing wave like this. Now, this is the one-lumper. I can get the two-lumper going. Looks a little bit more like a wave. And it looks like a real nice sine wave, doesn't it? Notice, how many wavelengths am I looking at here? I'm looking at one wavelength, right? Remember that a wavelength is the distance from any one point on a wave to the next corresponding point. Now I could also make the three-lumper. Here we go. See if I can get this one. It's a little bit harder. There we go. I think that's it. Yep, that's the three-lumper. There we go. Notice here we are looking at 1 1/2 complete wavelengths. Been working out with my shake-away. Let's see if I can get 4-lumper. Oh. Is that the 4-lumper? Oh, I don't know how many that is. It's a lot. Anyway, I can get the 1-lumper, the 2-lumper, the 3-lumper, the 4-lumper, and each one of those requires me to shake my hand at a very specific frequency. We see now that we're hinting at this idea of resonance, aren't we? Only certain frequencies create standing waves, right? And here we have, this is a fairly low frequency and a long wavelength. Notice I'm looking at half of a wavelength here. So the wavelength of this wave is twice the length of my spring. Notice this is a low frequency. When does this happen? When I match the driving frequency, the rate that I'm wiggling my hand, to the frequency that the spring wants to vibrate at. Now, it's interesting, a system doesn't necessarily have one natural frequency. We kind of presented it that way in the previous chapter. But this system has many natural frequencies, right? This is the first mode, and you'll see that the frequency is quite low. When I go to the second mode, you can see that the frequency is higher. Notice that I have to wiggle my hand at exactly the right rate in order to create this. If I slow down just a little bit, and it's actually kind of hard to do, then we don't get that nice pattern, right? So in order to get this nice pattern, I have to match my hand to the frequency that the spring wants to vibrate at. Again, I can get the 1-lumper. If I vibrate twice as fast as the 1-lumper, I can get the 2-lumper. Oh, there was the 3-lumper. Where's the 2-lumper? There we go. Twice as fast. If I wiggle my hand twice as fast as the 1-lumper, then I get the 2-lumper. If I wiggle it 3 times as fast, I get the 3-lumper, maybe. Oh, yeah, there it is. And you see, I have to find it, right? If I wiggle my hand too fast or too slow, the driving frequency does not equal the natural frequency, and I don't see this pretty pattern. Okay, so that's what standing waves are. We're going to talk about, so let's look at this PowerPoint, which has some nice pictures that are standing still, a little bit easier to wrap your brain around, potentially. So here we see a picture of the m equals 1 mode, the m equals 2 mode, and the m equals 3 mode. Be careful, a lot of resources will use n for this. You may even see me use n. Keep in mind, this is just an index, right? We're just counting which mode we are, and for a standing wave on a string, we're counting the number of lumps. So I call this the 1-lumper, the 2-lumper, and the 3-lumper. You will not see that language in the textbook, but it seems quite descriptive to me. We can describe these in a lot of different ways. Notice that as I increase the number of lumps, I decrease the wavelength. So here we see mode 1, mode 2, mode 3. Here we're looking at how much of a wavelength? That's a half of a wavelength. Here we're looking at one complete wavelength, and here we're looking at 1 1/2 wavelengths. Here we see a relationship then between the length of my string and the mode number and the wavelength. And you can see that if we just plugged in m equals 1, we would get wavelength equals 2L, exactly what I just described. If I plug in m equals 2, I get lambda equals L. My 2's cancel, and I have one wavelength fitting in here. And this could keep going, right? Now my arm's only so fast, so I was only able to demonstrate, up to about m equals 4. I might have gotten m equals 5 there for a brief second. But theoretically, at any rate, it goes on and on and on. We can then relate this to frequency, of course. Our big money wave equation still applies. Velocity equals lambda times frequency. Wavelength times frequency equals velocity. And recall that in general, the velocity is determined by what type of wave on what type of medium. So in this case, it's a wave on a string. We would need to know what the mass per unit length and the tension in order to calculate velocity, but we could do that if we had to. But at any rate, the point is that as I increased the mode number, I decreased the wavelength, and therefore the frequency had to increase. For that spring with that tension, the velocity remains constant. This is pretty much the math behind waves on a string. So this is pretty much all the math behind standing waves on a string. It can get a little bit confusing, but those are all the big ideas. The last bit of terminology that I need to mention is that these are the mode numbers right here. A node, so watch the language, a node, N-O-D-E, is where the string does not move. And so you'll see that when I do anything beyond really the one lumper, you'll see that there's this point here in the middle with the two lumper where the spring really doesn't move, right? At this point right here, the spring is really not moving. That is a node. Notice that this standing wave has three nodes. One at my hand, one where I've got it hooked to my chalkboard over there, and one in the middle. So the m equals 2 mode has 3 nodes. These points right here where the spring is moving the very most, those are called antinodes. So notice that this mode has 2 antinodes. 3 nodes, the mode number is 2. Here's a quick example. What is the mode number of this standing wave? Well, in this case, all we need to do is count lumps. 1, 2, 3, 4, 5. 5 lumps. This is the 5th mode. Now, we can get rules for this. Oh, well, we count the lumps, we count the nodes, and subtract 1. The problem is we're going to talk about a variety of different kinds of standing waves, and you'll need a different rule for every different kind of standing wave. Let's do an example. What are the 3 longest wavelengths for standing waves on a 240 centimeter long string that is fixed at both ends? You can contrive a situation where one end of your string is hooked to like a ring on a pole, and it can go up and down like that. We're not going to do that in this class. One can contrive that situation, but it turns out that the math is not that different. So we're not going to go there. So let's answer this question. What are the 3 longest wavelengths? So we are looking for, since it asks for the 3 longest wavelengths, we're looking for m equals 1, 2, and 3. And so we could just kind of plug that in. Well, 2 times 240 centimeters is 480 centimeters. Lambda 2 is equal to, well, that is, of course, 240 centimeters. And lambda 3 is 160 centimeters. Okay, so those are the 3 longest wavelengths for standing waves on a 240 centimeter long string, fixed at both ends. If the frequency of the second longest wavelength is 50 hertz, what is the frequency of the third longest wavelength? Oh, that's interesting. Let me clean up my board here just a little bit, and we'll answer the second question. Recall that we have this equation. The mth frequency is m times v over 2L, or the frequency of the mth mode, I could say. And so, what does this look like if I plug in F1? So, the frequency of the first mode is just 1 times v over 2L. Well, that's just v over 2L. So notice then that this could be written like this. And so I'm going to go ahead and find the frequency of the first mode, and I'm going to use that to calculate the frequency of the third mode. So that means that F2 is equal to 2 times F1. Okay, so that means that F1 equals F2 over 2 equals 50 hertz over 2. Well, that equals 25 hertz. Well, that means that F3 equals 3 times F1. 3 times 25 hertz is 75 hertz. Okay, not too bad. A really interesting application of waves on a string are stringed instruments, like this one. If I play this string, it's really a standing wave on a string. And so that is really the m equals 1 mode of a standing wave on a string. And under normal circumstances, that's how stringed instruments function. In the m equals 1 mode. But what's interesting is I can create what's called a harmonic, where I get the string to vibrate in something other than the m equals 1 mode. For example, here's the m equals 1 mode on my thinnest string. But if I stop it in the middle with my finger, I can create the m equals 2 mode. And you can hear that the frequency is higher. This interval is called an octave. The octave is identified as important in every culture that's ever been discovered. It's a higher frequency. It vibrates twice as fast. So an octave is defined as a note that vibrates twice as fast as another note. I can stop this string a third of the way along and create the m equals 3 mode as well. So m equals 1, 2, 3. I can even create the m equals 4. And I could probably keep going, maybe. Gets a little harder. There's the m equals 5. Ooh, there's the m equals 5, actually. Anyway, interesting stuff.